This video will introduce you to accessing Enki software resources using Jupyter notebooks. It will also serve as an introduction to the ThermoEngine Python package. Let's get started. From the notebook folder, open up a subfolder called Pure Phases. Pure Phases contains a number of Jupyter notebooks that illustrate using the Enki software ecosystem to calculate the properties of stoichiometrically pure minerals and fluids. The first notebook that is probably the easiest one to use and get familiar with the Enki ecosystem is the Compare Phases notebook. It's a Jupyter notebook that illustrates how to compute thermodynamic properties of quartz using a variety of built-in thermodynamic models that are part of the Enki package. Double-click on Compare Phases and open up the notebook. Every Jupyter notebook consists of cells that are either documentation cells or code cells. In this case, the documentation cells, which are fairly obvious here, compare stoichiometric phases, get access to thermodynamic database. These cells are written in a markup language called Markdown. And it's a very simple HTML-related markup language for producing documentation, including, as we'll see later on, LaTeX for mathematical equations. The other kind of cell in the notebook is a cell that contains code, and this is in this case, Python. Almost the entire Enki software package is accessed at the user level using Python commands. To execute cells in a Jupyter notebook, you click on the cell, hold down the Shift key, and hit a return. So, of course, that just executed the markdown cell, and you already see the markdown cell, so there's nothing interesting that happens there. But the next cell is sort of interesting. Here we're importing Python packages that have to do with plotting routines and, importantly, Python packages associated with the ThermoEngine Python package, which is the main Python package software implementation of the Enki software ecosystem. The Python packages, of course, wrap server code which is written in other languages, including C and C++ and Objective-C, but those are generally not exposed to the user. The execution of the cell is again Shift Return, and when a cell is executing, you may notice that the little brackets here enclose an asterisk when the cell is executing, and once it's finished executing, a number is assigned. So that cell execution brought in all of the relevant Enki software packages that we need for this calculation. The next cell is sort of interesting. It illustrates the kinds of calculations that can be done using Enki. In the next cell, we're going to create databases associated with the default database, with the Stick-Screwed-Lithgow-Bertoloni thermodynamic database, and with the Holland and Powell thermodynamic database for pure substances. There are other databases built into Enki, which we'll discuss in future videos. And there's a way of creating your own thermodynamic database, which we will discuss in the last video of this play series. By default, the database that's read in is the Berman database. When we execute this cell, we get Python instances of all three of those databases to use in future commands from the notebook or future execution cells in the notebook. If you're interested in more information about any of these ThermoEngine commands, the easiest way to do that is to use the online documentation. You can, of course, consult the ThermoEngine documentation on Read the Docs, which is good to do, and it's very comprehensive. But if you're programming online in a Jupyter notebook, the easiest thing to do is to add a cell to the notebook with the plus command up here. Come down and actually type the command that you're interested in. Or if you don't even know that command, type model, which is from the ThermoEngine package, the subpackage of the thermoengine package, type model and a period, and hit a tab character. And that will give you a list of all of the methods associated with that package. We're interested in the database command. We would like to know something about it. If you want information on a particular method, type the package name dot and then the method name and then a question mark and hit a return. And that will give you all of the information associated with calling that method in the implementation. Here you'll notice that the default database is Berman. This is Berman 1988. The default model for the silicate liquid phase associated with the Berman database is the original MELTS model. And then there are some other options to the method call that you can read about in the documentation. The important thing is that executing this cell now gives us access to all those databases. So let's actually use some of the information here. In the next code cell, we're going to grab an instance of the phase quartz from the Berman database, from the Stixrud-Lithgow-Bertoloni database, and from the Holland and Powell database. Phases, whether they be pure phases or solution phases in thermoengine, are accessed using abbreviations. This is a standard set of phase abbreviations that have been approved by the Mineralogical Society of America, but you may not be familiar with them. If you'd like information about all the phases in one of the Enki databases, or just what abbreviation is appropriate to use for a particular phase, the easiest thing to do is to print out a list of phases in the database by executing this command. Let's do so just for illustration. Let's stick a new cell in. Let's copy this command into that cell. And let's specify, as an example, the default database, the Berman database, to get a list of phases. If you execute that command by hitting Shift Return, you're going to get a list of all the phases available in the Berman database, their phase type, whether they be solution phases, which we will discuss in a subsequent video, or whether they be pure phases. And in particular, for every phase, there will be an abbreviation listed, which is the abbreviation that you need to use in order to access that phase in Enki. So let's come down and actually create an instance of the quartz phase from the Berman database, from the Stixrud-Lithgow-Bertoloni database, and from the Holland and Powell database. Now you'll notice that although all these databases are different and use different functional forms for the expression of the thermodynamic properties, they're all accessed in exactly the same way. And that's one of the great features of the Enki software ecosystem. All databases are accessed the same way using the same set of abbreviations. All the thermodynamic properties of all phases in all the databases are accessed the same way regardless of the database implementation. And that's very, very convenient. So by hitting Shift Return in this cell, we've actually created now an instance of the thermodynamic properties of quartz for the Berman database, the Stixrud-Lithgow-Bertoloni database, and for the Holland and Powell database. And just to make sure that we're not absolutely crazy, we can perform a sanity check, which will print out the phase name for each one of those properties, the formula. We should make sure that the formula is the same for all quartz phases in all the databases, and the molecular weight. And that may sound crazy that the formula may change, but actually for some phases, like the pyroxenes, some databases may implement a different total number of cations for the phase than others. So it's a good thing to check. Notice that this check was done by looking at the property of quartz Berman or quartz Stixrud-Lithgow-Bertoloni or quartz Holland and Powell. You access the properties, which is a dictionary, Python dictionary, and then the phase name or the formula or the molecular weight in order to retrieve those properties. There are lots of other properties that are available. Again, if you're interested, just look at one of the databases, let's say Quartz Berman, and look at the property of that database. And if we just hit a return, you'll see all the different properties that can be accessed. I happen to grab the phase name or the formula and the molecular weight. But if there was some other property that you wanted, like the abbreviation, for example, you could pick up the abbreviation from the dictionary and print that out. As I said, all thermodynamic databases that are available in the Enki software ecosystem, and in fact all thermodynamic databases that can be created using the coder and codegen modules in the Enki software ecosystem, are accessed in exactly the same way with respect to their thermodynamic properties. So all phases, all pure phases, will have available the Gibbs energy, the enthalpy, the entropy, heat capacity, and volume, and then various derivatives of those quantities on demand. So to illustrate using those, let's just take a look at the heat capacity of quartz as expressed by these various databases and plot that up against some data on the heat capacity of quartz that are available from the literature. We're going to pull data on the heat capacity of quartz from a publication that was produced a very, very long time ago by this obscure individual named Ghiorso. We're going to read those data in. Those data are available in disk. They happen to be the file Ghiorso cpquartz.txt over here. We're going to read those in, and then we're going to calculate the properties of quartz using Berman, using Stixrud, Lithgow, Bertoloni, and using Holland and Powell. Each of those databases, the heat capacity is accessed in exactly the same way. We're going to calculate those properties over a variety of temperatures corresponding to the range of temperatures for which we have data on the phase. The Python, which is included in this execution cell here, is pretty standard Python. The temperature array is calculated using a NumPy temperature array from 250 to 1200 degrees Kelvin in 100 Kelvin increments. The heat capacity expressions or the heat capacity modules are accessed by passing that temperature array and either a pressure array or a pressure value to that module, to that function. And this array will then come back and contain the heat capacity values according to Berman, Stixrud, Lithgow, Bertoloni for the next one, and Holland and Powell for the next one. And we're going to use the matplotlib package to actually plot those packages up. If we do shift return, all those calculations are done and retrieved and plotted in the plot that you see. We could change the temperature range or change the pressure range by simply inputting different values to those functions. I'm not going to discuss in detail here the various calls to the plotting routines. If you're interested in that, you can go look up documentation on the matplotlib library. We can look at other thermodynamic properties of quartz using different function calls. For example, the entropy at 1 bar, which can be computed and compared to actual data points from the CODATA resource. And here the calculations are done. The data point is here. The various curves, which are labeled in red from Berman and in blue from Stixrud, Lithgow, Bertoloni, and yellow from Holland and Powell, are plotted there. And we can go through and do similar calculations for all of the thermodynamic properties that might be of interest. The Gibbs energy, the enthalpy, the volume, and its various derivatives. You'll notice on each of these plots that the measured property is compared to data retrieved from the various databases. And you'll notice that there's some discrepancy here as to the agreement between database values and the actual measured property. And that's, of course, because each database has been calibrated on different properties, on different assumptions, and has been calibrated to emphasize different conditions. A really good example of this would be the Stixrud Lithgow-Bertoloni database, which is really applicable to high pressures and not low pressures. And here we're comparing low pressure heat capacity data to the Stixrud Lithgow-Bertoloni database, and you can see that there really is very, very poor agreement between the data and the actual database retrieval values. And that's really by design of that database. It emphasizes that it's important to use a database which is calibrated and is designed for the particular thermodynamic application you're interested in. In this case, low pressure heat capacities are better retrieved by Berman and by Holland and Powell than they are by Stixrud. And we're going to see an example of that in a second, and particularly having to do with the volume. We can see that the low pressure volume measurements are best retrieved by looking at data from Berman and from Stixrud Lithgow-Bertoloni, whereas Holland and Powell do not recover the low temperature volume of quartz according to measurement, but they've optimized that volume of quartz to retrieve the higher pressure properties correctly. So again, it really depends on what you're interested in determining your choice of database to use. But importantly, the Enki software ecosystem allows you to investigate all of these databases and plot them against each other and decide which one is appropriate for the application you're interested in. And as an illustration of that, let's look at the volume properties as a function of pressure for quartz. Here, you see that the Berman properties, again retrieved and plotted in red, show very, very unusual volume behavior at high pressure. And that's because the Berman thermodynamic database is simply not designed to retrieve the properties of minerals at high pressure, particularly for pressures on the order of a gigapascal or so. And you can see that the database retrieval from Berman deviates substantially from the database retrieval from Stixrud, Lithgow-Bertoloni, and Holland and Powell, which are the preferred databases for high-pressure mineral properties, particularly Stixrud, Lithgow-Bertoloni, to very, very high pressures. And again, if you look at derivatives of the volume, you'll see very similar kinds of behavior, which indicate how these various databases were calibrated. So in general, or in conclusion here, the Compare Phases notebook shows you shows you the ways in which you can retrieve thermodynamic properties for pure phases using Enki. It illustrates how to do that using 3 different databases that are built into the Enki software. And it also allows you the opportunity to compare database retrieval from these various databases and decide for your own application which is the more appropriate database to use. Now that we've spent some time looking at the calculation of basic thermodynamic properties for a phase using the various databases available in the Enki software ecosystem, one last thing that we might want to look at in the collection of notebooks in the Pure Phases folder is a notebook that illustrates calculating the properties of a reaction and plotting up that reaction as a univariate curve. There are a couple of notebooks that illustrate this, the phase diagram notebook, the plot reaction Stixrud notebook, but the simplest of these is probably just the plot reaction notebook, which allows you to plot the properties of a very simple reaction using the Berman database. So let's open that notebook by double-clicking on it, as I've just done, and let's take a look at some of the code. Again, it's a Jupyter notebook, so it consists of Markdown cells and Python cells. We'll execute those cells in order. Here, we're simply reading in the relevant thermo engine packages that we need, the phases package and the model package. We're reading in some NumPy packages to do the numerics, and of course matplotlib to do the plotting. The next command should be familiar to you from running the compare phases notebook. This just instantiates the Berman database. And again, if we wanted to know abbreviation names and so on, we would interrogate those using the commands that we've used previously. But now, unlike the previous notebook, instead of retrieving the properties of a single phase, let's retrieve the properties of a collection of phases and write a reaction between them. Let's retrieve the properties of forsterite, a quartz, and clinoenstatite to form a chemical reaction. And that reaction is going to be forsterite plus quartz equals 2 enstatites. Again, the assumption is that the stoichiometry of enstatite is MgSiO3. The get reaction command here, you can look at the documentation for this, but it consists of 2 parts. First, specifying the abbreviations as a Python list, and next specifying a collection of zeros, which correspond to the fact that every one of these phases consists of only a single end member, so this is the 0th end member of those phases. This reaction routine can be used for solid solutions, so you can have higher order end members, or you can have more than one end member of each phase. And then the last consists of the reaction coefficients. It's a -1 because you're consuming a forsterite, -1 because you're consuming a quartz, and +2 because you're producing 2 enstatites in this reaction. This method will retrieve essentially an object which corresponds to the reaction object. You may get a deprecation warning which will disappear in some future version of the software. And now we can plot up this reaction by again specifying a temperature array using the NumPy array generator. This time we're going from 500 to 2000 degrees centigrade, converting it to Kelvin and storing it in this array called t-lims. And then we're going to produce a univariate curve by feeding this series of temperatures to this method called trace boundary, which is a method of this reaction class. And we're going to produce 100 points as a sample along that univariate curve. And now we'll plot the curve. And so it's really as simple as that. You can define a univariate curve using the reaction stoichiometry. You can then do that calculation in temperature, pressure, space. And if you had a series of univariate curves, if you wanted to build up, for example, a pseudosection, you could do so by simply plotting multiple univariate curves on the same graph. Now that we've taken a look in some detail at the Compare Phases notebook and the Plot Reaction notebook in the Pure Phases subfolder of the Notebooks folder, I urge you on your own to take a look at some of the other notebooks in this collection, including the forsterite Stixrud notebook for the calculation of the properties of forsterite at high pressure, to give you an idea of how that's done, and also the phase diagram notebook, which shows how to calculate a phase diagram for the aluminosilica system from the database of Berman using the Enki software tools. One other notebook that you might want to take a look at is the water notebook. We're not going to go through it in detail, but let me double click on it. And the reason this is interesting or useful to examine is because it discusses a little bit about the standard water integrated model, which is part of the Enki package. There are various thermodynamic models for water, some of which are applicable at high temperatures and high pressures, some of which are applicable at low temperatures and low pressures. The Enki swim model, which is the standard water integrated model, is an attempt to meld various water models that are available in the literature into a comprehensive model which can be used over the whole of temperature, pressure, space. And if you're interested in the properties of water and you plan to use them in some of your calculations, I would execute this notebook and go through some of the details to show which model is being used in which portion of temperature, pressure, space, and whether or not that model is applicable to the sorts of calculations that you're trying to do. That's it for this video. In the next video, we will examine MELTS calculations using Jupyter notebooks in the Enki structure, and that will be an examination of some of the notebooks in the MELTS PMELTS subfolder of the notebooks folder. Thanks very much. See you next time.